Thanks for coming, guys. Before I introduce the distinguished panel, if you'd like to support this channel, there's PayPal and Patreon links in the info box below. And this is going to be a rockin' topic tonight. Epic. But before we get to that, our distinguished panel. Betty Van Velsen, how are you today, ma'am?
Yeah, I'm great. Thank you. Thank you for inviting me.
You're very welcome. We have the distinguished Nathan Oakley.
Thank you for having me, sir. Good to be here.
And the distinguished D. Adam Meakin from Iron Realm Media.
Good evening, QE, and good evening, everyone. Lovely to be here. Looking forward to a little bit of spectroscopy this evening. So,
and Dr. John D.
Hello there. Hi from the South Coast, and it's really good to be here and to talk about my favourite subject, spectroscopy.
Increase the enthusiasm now.
Oh.
And last but not least, Anthony Riley. How are you, sir?
Yes, master.
So how are we all doing today? Are you ready for spectroscopy?
Yes.
What did you say?
Spectroscopy. That's what it is, or spectroscopy, or spectroscopy.
no, it's been redefined and renamed. The ball has started it, but we'll define it properly. Spectroscopy.
And what else we got going?
Yeah. Yeah, it took me 4 years just to say that word right.
It's taken at least 6 years, and they still haven't got it right on the Baltard side. It's a joke out there, folks. What are you guys doing? That's what I want to know.
Yeah.
So what
Well, at least I have an excuse.
And what's your excuse?
I'm Dutch. It's
That's not,
difficult for me.
that's not an excuse. Where are all the Americans on this panel?
Yeah, I think that I can say it now, but if you go on with these different words, I think I can't. So hopefully I'll learn something more about spectroscopy today.
Yeah,
Is it different in Dutch then, Betty?
Sorry?
Is it different? Say it in Dutch.
Spectroscopy.
No, spectroscopy. That in Dutch.
Well, that's only one color. That's brown, right?
There's many shades of brown,
50?
at least.
Hey, so listen, I wanted to bring this subject up. My mistake, and it's my shortcomings, that I haven't brought this up, in the recent past. I did it indirectly with the CMB presentation that I did on Cathexis's channel, but like I said, that was just indirectly. So I apologize for everyone out there for not doing it, but we're going to get it done today. And we're going to show you what a fiasco this is. Now, not spectroscopy. That's a legitimate discipline. We're going to show how astronomical spectroscopy or celestial spectroscopy is just a bastardization of it. It's a joke. Recently, you've been hearing a lot of these ballers if they're saying with spectroscopy. I know you guys been hearing it, and all they do is say the word, right? Or try to say the word. But there's nothing underneath it. They don't even understand it, right? So I don't know. Have you guys been hearing it as much as me, or is it just me?
It's normally a one-word defense to a question like, what's the sun? Something so simple. Well, we know exactly what the sun is. How do you know? Spectroscopy!
Yeah,
I'm with you on that, guys. I think, like many things the ballers do, they'll pull out a word that's associated with science, use it to validate, blindly validate their previous assertion. And for me, the interesting thing is what spectroscopy you're talking about. Are we talking celestial or real spectroscopy from somebody that used it in labs? Nowhere near as qualified as the next person that should speak, Dr. John D, with regards to it. But for somebody that used it in labs, it was a very precise piece of equipment that we would use that was validated with some science. But to support that science, extreme control was required for us to then draw any inference from the technology we used based on that science.
Yep, for sure. Have to back you up there. 3.5 years of me doing spectroscopy PP. Like highly controlled. You know, we use like those machines. You know, the environment had to be clean. We had to know, you know, like what was around us within like the environment. We had to clean our, you know, we had to clean the environment like we cleaned it. You know, like not cleaners, just to make sure it was all like really clean. Which I think might be slightly different when you just you know like look at the stars. I'm not sure how clean the environment is, but like let's wait and see.
But has anyone challenged you directly, Dr. John? That's what I'm interested in.
No, like no one's challenged me directly. Like what would they challenge me on?
I mean, would they? Maybe you're in a discussion and it gets around to the topic of, oh, we know what the sun is made of. And you're on the panel or you're in the discussion or hangout. Has that happened?
No.
Yeah,
not yet.
Yeah. All right. What about you, Anthony?
Sorry to interrupt there, John. Just one last question for John. John, what's your PhD in?
Spectroscopy.
All right, that's it. Sorry. Carry on, guys.
Just before you move on to Anthony, I just want to get something clear off the bat because it will hopefully help me maybe reach a wider audience in this regard in debating terms. So spectroscopy is a discipline or a process that you would employ, a technique, if you will, as opposed to an answer to a question. It's akin to saying, well, yeah, I do know how to cure cancer. Well, how do you cure it? Medicine. It's not a reasonable answer to say spectroscopy as an answer. In other words, what did you actually do? You know, using that technique. Like we've got onto the very early stages already in the discussion about keeping things clean during the process, but it's not an answer to a question, if that makes sense.
Yeah, it makes perfect sense. Anthony, have you been challenged with this also?
Not really challenged directly with spectroscopy, but I have been challenged when you say what's the sun made of, and they go spectroscopy tells us that it's made of A, B, and C. It's the same argument for seismology, telling us that the molten iron core is X amount of characteristics away from us or whatever. I've seen different people claiming that seismology proves that we're on a sphere because of primary and secondary waves. And we've all seen the Conspiracy Cats illustration, the little cartoon thing that he claims is the only possible shape it could possibly be is a sphere. It's the same kind of thing that we're talking about now. So basically, it's kind of like when they say space-time, it seems to be like the top trump card that as long as they say space-time in their answer, it sounds like they can get through any criticism. Spectroscopy proves blah, blah, this and blah, blah, that. So it's a buzzword. It's probably always used out of context or probably flippantly used when it shouldn't be flippantly used. And no one really, I mean, as far as I'm concerned, nobody in the topic really understands anything about it, but they use it as though it's like a policeman's warrant card and they flash it out and then they can run through walls with it and stuff like that. So I'm here to enjoy the what are we going to learn from this angle?
It's a lot like gravity, right? It's one of those trump cards that answers all questions, right? Well, gravity.
Yeah.
Refraction.
Yeah, it's so true.
Spectroscopy. spectroscopy and spectroscopy. So, are we ready, gentlemen?
Yeah,
And
reminds me of the word refraction. It seems like spectroscopy is the new word.
Yeah.
And it sounds sciencey, right? It sounds like they know what they're talking about. But it's just like with anything else, right? Once you dig underneath the surface of these terms that they flippantly fly out of their pie holes, and it all goes to squat, man. They don't got anything, do they?
No.
Right, without wanting to sound like 10th man, can you throw some light on this subject, please?
Yeah.
Shout out to 10th man.
Yeah.
Yeah, what kind of light's that? UV, the infrared,
Is it continuous?
visible.
Is it a continuous spectrum? Is it an emission spectrum or an absorption spectrum? No, we're going to get to that here in a few seconds. All right. So, one of the more common Dunning-Kruger spinning ball-tard space monkey wiki Discovery Channel mindless parrots we've all heard. We know what the sun is made of. Spectroscopy or spectroscopy. Or according to Toady, Grody, the lion retard, just last week, my favorite, spectroscopy. That, sir, is a catastrophe. Okay? Let's let him say it.
Right, so what they found was they found spectrum lines, like we looked at the other day from spectroscopy.
Yeah, that's what we got. Go ahead.
I said too funny.
Yeah.
Say
Spectroscopy.
it.
Yep, it's a catastrophe. So, we're going to start off with, this is very important, key learning objective number 1. Gases only emit and absorb in bands. One got that. We're going to hear that again coming up here over the entire presentation. Oh, spectroscopy. What is it? Basically, it's the interaction of light with matter, specifically with respect to emission and absorption of radiation. The entire enterprise is based on the quantization of energy, quantum mechanics. Each element has its own unique, distinct fingerprint, governed by the number of electrons and their shells or energy levels. So we'll take a good look right here. As you can see, this is, like I said, I don't want to go into any great depth here. We can get off on many different tangents, but a typical hydrogen atom, right? It's a lot like us. It likes to stay in its relaxed state or the ground state. However, sometimes it gets excited. Sometimes we like to run marathons, but we can't do that all the time. We always have to return back to the ground state. And that's what atoms like to do. So what happens is when this atom or any atom absorbs a discrete amount of energy, it has to be a discrete amount or it'll just transmit through to reach the upper energy level, right? Once it does that, once it gets that unique amount of energy and kicks up into the higher energy levels, right? It always wants to come back down to the ground state. Now, when it absorbs a certain amount of energy, like I said, has to be a distinct amount, it jumps up into that higher energy level. But when it comes back to the ground state, it bypasses this space in between and it arrives here, right? This is the entire basis of spectroscopy and one of the main foundations of quantum mechanics, right? And it'll only release a certain amount of energy. Okay, and here's a better look at it. The hydrogen.
John, before you
Sure.
do that, can you just go back to the other one? Because if you look at that diagram there, you look at the electron, the absorbed energy, and the arrow of transmissions it moves from one orbital into the next. And I just want to clarify that point. Whilst there appears to be an arrow there and it appears to be the electrons moving, there really shouldn't be an arrow at all. There should just be two X's. there is either absorbed energy in the lower ground state, which then relates to the electron appearing in the outer shell, in a higher energy state shell. There's not a transition. I know that's relevant to the next point, and I think it's really worth exemplifying that this electron doesn't glide from position A to B in any transitional way. It either is in the ground state or in a higher energy state. It's one or the other. There's no transitional positions for an electron.
Exactly. Go ahead. Anyone else?
Yeah, but mine's the kind of, I don't really understand any of what you've just said kind of question, so I'll wait for the gap.
Maybe after I get done explaining it down here, it'll be, you can better understand it. We'll go back to the hydrogen atom. So as we can see here, now don't pay any attention to orbits. There are no orbits here. Just call them energy shells or energy levels. As you can see, if the hydrogen atom gets excited, it'll kick up into the higher energy levels, right? So let's say the hydrogen atom absorbs enough energy to bypass the blue-green and head up to the violet, right? Or N4 or N5, whatever it may be. Now, when this electron comes back down to the ground state, if it came from this point and passed through the space in between the violet, blue-green, and the red, you see this emission spectrum right here? This would be one big smear instead of individual lines. That's the dead giveaway, right? Does that help out a little bit?
Absolutely.
Any questions on this right here? Adam?
I've got one question. Sorry, Adam. So what you have presented then, I know you've appreciated what you'd have if it's moving between these energy states. You'd have a smear in terms of these, rather than these defined lines. So is it relevant what the defined lines are at this point or not?
It is, because each element has its own distinct energy levels, and we could tell what element is it from its emission spectra.
Based on its neutral, what's the word you used again? Not neutral state, base state, was it?
Based on the energy levels. These energy levels right here, they're all distinct to each element.
But at its relaxed
ground state.
Ground state, that was the one. Thank you, John. Ground state. Okay, so the ground state is what would give you this distinct line rather than a smear as it's transferring, going up or down in energy. Okay, I'm with you. Yeah, brilliant.
Well, the ground state isn't giving you these emission lines. It's the electron coming from its higher energy levels back down to the ground state. Or did I just...
Oh dear.
Or, yeah, I probably just confused it.
Then, no, it's not clear. So why would you get a smear then? Because presumably it's having to go up to that energy state and back down again. Wouldn't they all give you smears? Or is that transition only as big as that band in each of these pictures on the bottom left?
Right. As you can see here, as this, let's say an electron gets kicked up into this energy level, and let's say it went down, it passed through the space here, right through the blue-green, right through the red, back down to the ground state. You see this picture here? This emission line spectra? This would be, instead of having distinct lines, it would be a smear all the way to the red from the violet. Smear. So, since it's only distinct emission lines, this electron moved from here to here without traversing the space in between. It's called the quantum leap.
Yeah, so that kind of, this is the kind of experimental validation of what I just hypothesized previous with regards to electrons. They don't glide from one, we use the term shell, from one shell from N2 to N3. They don't glide and have any transitional position between N2 and N3. They are either in N2, a lower energy state, or they're in N3, a higher energy state. There is no transition. So the proof of that is within this spectra where, as John's saying, if they were gliding between the two, having transitional positions, you would see, like say, a blurring, a spectrum across there between the two energy states that's highlighted. Does that make a bit more sense now?
Yeah, it's digital. There's no analog in between.
Exactly.
Yeah.
Exactly. You got it. Okay. There are three main types of spectra: continuous, emission, and absorption. Continuous spectra are produced by energized solids. Emission lines are produced by energized thin gases without a light source behind them, and absorption lines are produced by cool, thin gases. I'm up here. The absorption spectrum and the emission spectrum are flip sides of the same coin. If this element, hydrogen, emits in these wavelengths, then guess what? It also absorbs in those exact same wavelengths. No difference. Any questions here?
Yes, but maybe give the others a chance, or shall I just go? I mean, the key point for me is just solids, liquids, gases, and I know you've got it in brackets there. Solid and liquids is just, John probably explained better. There are sort of differences, I suppose, between the two that allow you to deal with it. But for most points, solids and liquids in this concept are the same. The differential point is the way gases behave. And I would maybe just, John, could you, Dr. John, could you just elaborate on, for me, just to help me, the difference really in layman's terms of the way those spectra apply to gases and solids and liquids?
Well, with the absorption and like emission spectrums, we're talking about the individual particles, can't we? And then with like the solids, because the particles are so like close to one another, they then start to interfere with their discrete like jumps. The energy shell jumps kind of no longer are like separate like from each other. But when you've got them as a pure, when you've got them like separated like from each other in the gas, you can see those like separate jumps. Is that making sense?
Yeah, because the atoms are so close together, when they get really excited or really hot, they start to vibrate out of their minds, right? And what happens is you got all that kinetic energy and you got those atoms overlapping each other. You get a continuous spectrum. It becomes smeared, right? But with gases, they're thin and they're separated. The molecules aren't close enough to each other to produce a continuous spectrum. How about that?
Yep, sounds good.
Floats my boat.
All right. Key learning objective number 2. Gases only emit and absorb in bands. Everyone got that? Now we get to the rub. We have terrestrial spectroscopy versus astronomical or celestial spectroscopy. With terrestrial spectroscopy, we have atomic emission spectroscopy, AES, and atomic absorption spectroscopy, AAS. Right? Let's take a look at these. Pay real close attention to the juxtaposition. Terrestrial spectroscopy, atomic emission, like I said, AES, we have flame, inductively coupled plasma, electrothermal, that's a graphite furnace. And if you notice right here, inside a frigging machine, it's a closed system, extremely highly controlled. This one is inductively coupled plasma atomic emission spectrometer, right? And these are uber expensive, people. I'm telling you.
I'll tell you what, John. The ones I alluded to using ones in labs, they weren't that bad. I bet Dr. John's use similar equipment, but that looks a fancy bit of kit.
I just want
No,
to.
it doesn't. It looks like a white. It looks like a white box. What does it do?
We're going to look at that here in a second.
Okay.
Yeah, you're probably talking about £100,000 or something like that.
Yeah, the important point that I want to leave you here with both the terrestrial spectroscopies are it's a closed system, extremely highly controlled. Remember that this is self-evident and plainly obvious. Now, I'm not going to get into the nuts and bolts of this. I just want to give everyone an overview so they can understand what's going on here. So you have the analyte, the thing that you're trying to discover what it is, mixed with a solvent, is aspirated inside this mixing chamber, along with the fuel gas and the oxidant. Things are mixed up in a nebulizer and aspirated via the nebulizer into the flame. Now, this is an emission spectroscopy, right? So what happens is the fuel gas gets burned off and the oxidant evaporated. All it's leaving here in what they call this is the atomizer, right? All it's leaving here is the analyte. What it does is turns as an atomizer, separates them into individual atoms and then turns them into their gaseous state. Why? Because gases only emit and absorb in bands, right? You're going to get an emission spectra on this detector right here. Everyone got a grasp on this. This is very important. Good?
Yeah, I've got a quick question. So presumably, point 1 is on the right-hand side of this piece of equipment, this feed, which looks like it's got a tube into liquid. But based on what you've said, does it mean you can do it with anything, gas, liquid, or solid?
I'm sorry, I was on mute. It's for solids. You're going to convert it into a gas.
Fine, just solids. Okay.
The reason we're doing this, Nathan, we're taking a solid. If we took a solid as described in those previous spectra, you wouldn't be able to analyze it as itself. So what you need to do from a analysis point of view is what's happening here. They're nebulizing first, making it into small air-bound particles, and then breaking those down even further to atomize it so that it becomes a gaseous state. You then stick it in the flame and stick the light analysis through, put simply. But it has to be gaseous for you, as described previously, to get that emission the spectrum. Sorry, the word's gone.
Yeah, I get it. To see it jump from shell to shell,
Yeah.
It's got to be far enough apart in and of itself to be able to see that, rather than it smearing up because it's a solid gas, as a solid structure with all of them nicely typed together, and then you'll just see an overlap. Whereas if you vaporize them, then you've got a gas where you've got enough separation between them so you can see these nice distinct lines.
So we want to analyze a solid, but we can't analyze solids, so we have to turn it into its gaseous form for us to be able to analyze it via spectrochocoloscopy. You cannot analyze solids because they don't give you an emission. They don't give you they don't give you the correct spectrum for you to be. They don't give you anything. You just get a solid lump of data. You're not getting the data. John, maybe you can just fill.
Which John?
No, sounds good.
Oh.
Sounds good. Yeah. You have to put it into the gaseous form to separate out the particles, so you get those like sharp, those sharp like bands of light. Like you say, if you don't, you will just get a whole smear across, the whole spectrum. So you won't be able to like recognize, like what you've got there.
Thanks.
And hold on a second, Nathan. You said now it doesn't have to be a solid; it could be a liquid also, right?
Yeah, but presumably if there was a cock-up in the procedure and it didn't atomize correctly, then you'd know it because you'd get the smear as well, right? Even if it hadn't been broken down enough.
Say that one more time.
So if this process in some way went wrong and it didn't fulfill the process properly and it didn't make it into small enough particles to combust, then again you'd just get large particles that were interfering with themselves, and you get a smear also. So it's quite,
I see. Yeah.
So the precision of doing this is critical,
Brilliant,
which is probably why it costs £100,000 to do it. Because if you're doing it in a cheap way, it's not gonna separate out to the point that you can get your nice tight bands of light to actually analyse the thing. It's just going to be a great big overlappy smear of not correctly vaporized particulate matter that's not a gas, when that's what you're actually needing to study.
You got it, exactly. And there's so many controls, and there's so many ways that the sample can get, how would you say, compromised. And Dr. John spoke about those before. There's so many controls. You have to keep everything clean. Everything is down to a gnat's hair. Right, Dr. John?
Yep, that's what you get paid for.
All right.
So I hear something like variables and things being controlled and stuff. So is this then science, John? QE?
Is this that's a great question. Let's put that to the panel. Is spectroscopy science? Right here. Is this science?
It's a piece of apparatus. So yes, you could easily formulate a hypothesis and then utilize this technique to establish the cause of an effect. But it's equipment and methodology as opposed to a hypothesis. So it's a bit unreasonable to say, is this science? Well, no, we're talking about a piece of equipment.
I think I carefully used that analogy earlier in one of my rambles, and I was careful to do so to point out that this, whilst there is science behind the construction of this piece of equipment, this is technology and analysis, and there is real science that was used in its construction, and that gives it validity to its results. But if you switch the machine on and stick some on and atomize it, and then do a bit of spectrochocoloscopy on it, are you doing science? No. You're operating a piece of equipment that's already validated by science, and you're getting a result out. That's not doing science.
Okay. Dr. John D., you got anything to add? We got 2 no's. Go on. Hello?
Hello, sorry about that. Yes, because I suppose it depends what you do. So if I had different, like concentrations of, like, say, strontium, I could then say, okay, so as the concentration gets stronger, the intensity of light gets brighter.
Okay.
So is that a cause and effect?
Is your answer a yes or a no?
Is it science? I'd say, yeah, the machine itself and what it does is not science. It depends how we use it.
Okay, fair enough. Anthony, is this science?
Is there a manipulation of the presumed cause?
That's a good question, huh? What's the cause? What's the effect?
All right, so remember my 2-step algo. My first question was, is your inquiry concerning cause and effect how, why questions, or is this inquiry a what is question? What are we doing here? We're trying to find out what. We're trying to find out what this is, right?
We're measuring something.
Well, like I said as well, you could be measuring different, like, concentrations of the same thing.
That's a what is question, right?
John, can I have a bang on that? So this is a what is question. What is this? Okay. This is not a cause and effect relationship. However, you could use the data from a what is, and as Dr. John alluded to, titrate things to start to build a hypothesis towards a cause and effect relationship and show those things. So it is a piece of equipment that is validated and constructed through scientifically validated knowledge that you can then use later on to further scientific discovery. But the operation of the piece of equipment in of itself, for me, doesn't mean you're doing science. It means you're operating a piece of equipment. It could just as well be a lathe, driving a bus. You're operating a piece of technology. The way in which you take that data to try and support any cause and effect relationship you're presupposing. But this, in effect, is a tape measure, isn't it?
Yes. Answering a what is question. Yes.
Yeah.
Got it. All right. The second one. So we went over atomic emission spectroscopy, right? Side of that coin is atomic absorption spectroscopy. Right? We got flame, cold vapor, hydride generating, and a graphite furnace. And again, inside a friggin' machine. Closed system, highly controlled. You're looking at here is a flame atomic absorption spectrometer. Same type of deal, right? Yes. Now, we're going to look at the same setup. Remember the setup that we had above that illustrated emission spectroscopy? Well, doesn't this look the same? There's only one difference, right? Because we got the analyte sample thrown into a mixing chamber with the fuel gas and the oxidizing agent. These are all mixed up, right? And nebulized into a nebulizer and then aspirated into the flame. What's the difference here between this and the other one? We have a cathode lamp or a deuterium lamp that shines a light through this gas. And because gases only emit and absorb in bands, remember our learning objectives, we get an absorption spectra. Any questions here?
No.
Make sense?
Yep, makes sense.
Now, those up above are terrestrial spectroscopy, as opposed to celestial or astronomical spectroscopy.
Whoa, John, what's that? That's just like sticking out the top.
Yeah.
Into the atmosphere. Where there's, like car pollution. Whoa, like that's hardly closed, is it? Like, what's going on?
Yeah. I was
ahead.
going to ask a similar question, because up until now we had a running theme about being very controlled and closed and inside a machine and terms like that. And yeah, then we get to this, but John's already he's way ahead of me. So yeah, exactly. I echo that sentiment.
Well, can I just jump at Nathan? This is where we got battered on one of your shows the other week. So I suggest we do the same, because we're about to do the same, but we kind of, the power, not just John's research, but actually the power of your debate, we stumbled on this and came across this point, and that's why I got an arse kick in. When he was being really funny with us. Shut up. Don't talk about this.
Yeah. I tried to get you off.
Yes, I do. Yes, now I do. I didn't, but now, yeah.
We're about to do the same.
Oh, you're going to recognize it here in a minute, right? You're going to get it.
Is that looking at the sun?
Yes. This is the McMath Pierce Solar Telescope from Kitt Peak National Observatory. It is the one that conjured and calculated the famous absorption spectrum of the sun. That we're going to see that below in a few minutes.
But it's looking at the atmosphere as well, isn't it?
Yes.
It's not just looking at the sun.
No. Does it know between the detector and what it's measured? You have to know the makeup of everything in between the spectrometer and the detector.
Yeah, agreed.
So,
hold on, that leads me to another question. I'm really sorry to interrupt.
No, go ahead.
So, who's operating this? And the reason I asked that question is because are the people who are operating this under the impression that the medium that they are looking through is a second law of thermodynamics violation sky vacuum? I just want to know who's operating it and what they believe in that regard. Do you know?
Yeah. They think it's a vacuum. They're heliocentric baltards. Yes. Yeah.
That's a big problem.
Yeah.
I've got a question.
I've got one first. Dr. John, If I was to put this to an actual spectroscopist in the lab and showed him astronomical or celestial spectroscopy, after we just went through atomic absorption spectroscopy and atomic emission spectroscopy, what kind of answer can he give me when I say, well, it's extremely highly controlled in a closed system, and then I throw an open system at him that's not controlled?
I think they would say, do you know what's between you and the thing that you're looking at? Because if you don't, please just turn off that machine now.
John, can I ask you an analogy then? If back during your PhD stuff, you'd have presented your data to support your whatever you did within your PhD, and that data, instead of being analysed through those amazing looking machines, you'd have sat there with your sensor at one end of the lab and a Bunsen burner, and you're burning the stuff at the other end of the lab. What validity would your peers have attributed to the data that you had collected?
Yeah, I don't think I would have got through, to actually do my Viva. I don't think my supervisor would have set my Viva up.
Okay, so forget that then. Instead of just that, you took a toilet roll, put it on the front of the sensor, and pointed the toilet roll at the Bunsen burner. would they have liked that even more?
Yeah. They might be, they might be a bit concerned about light from the, like from the lights, within the room and things like that. I don't think I could have got away with that, Adam. Worth a try, like stuff like that is so much like cheaper, than buying these, £100,000, like pieces of equipment that you have to close the door to make sure it works, in the dark. But I'm not quite sure what's going on here. Surely they would have to know what's within like the atmosphere.
I'm with you.
So just maybe I'm being dumb. So when the globetards say spectroscopy answers all of these questions, they're actually loosely comparing this garbage, which isn't in any way controlled study, to actual spectroscopy. And the difference is celestial versus, would it be called terrestrial, John?
That's what I term it as, terrestrial spectroscopy here versus celestial spectroscopy. I'm looking at the object that they're looking at, not where they're at.
I mean, I just don't want it to be descended too far into farce, Dr. John. So I know you were given an analogy with setting bog rolls on fire, but just for a more reasonable comparison, the 10 or £100,000 box that we first saw that I said doesn't look posh, it's just a white box, but very much a closed, sealed box. I don't know if John's going to get it on screen. Here we go. If that was in some way opened up, so forget about it looking through the room's atmosphere, but just if the box was open, would it give you a valid result?
No, because light would get into the detector and it would, like forget it. Forget it.
So if your box, is spectroscopist the correct term? When you were a spectroscopist,
yes,
your box wouldn't be like the one on screen now, in any way allowed to be open?
No.
Okay, thank you.
All right. So obviously we just went over the number one belly laughing train wreck, right? It's an AKA Mr. Magoo false equivalence fallacy between terrestrial spectroscopy and reasons we just went over. They don't have anything to do with one another. Number two belly laughing train wreck from Focal Peter Solar Astrophysics and Cool Cosmos from Caltech. Astronomical spectroscopy is used to measure three major bands of radiation: visible spectrum, radio, and X-ray. While all spectroscopy looks at specific areas of the spectrum, different methods are required to acquire the signal depending on the frequency. ozone, O3, and molecular oxygen, O2, absorb light with wavelengths under 300 nanometers, meaning that X-ray and ultraviolet spectroscopy require the use of a satellite telescope or rocket-mounted detectors. Radio signals have much longer wavelengths than optical signals and require the use of antennas or radio dishes. Infrared light is absorbed by atmospheric water and carbon dioxide, so while the equipment is similar to that used in optical spectroscopy, satellites are required to record much of the infrared spectrum. So, since X-ray, ultraviolet, and infrared spectroscopy require satellite rocket-mounted telescopes, i.e. need to travel into a second law of thermodynamics violation, aka telescopes in Narnia, they are shit-canned. Our focus is on the sun, radio spectroscopy is also shit-canned. So, for the section summary, when the incoherent hordes of clinical-level Dunning-Kruger pretender clown wiki Discovery Channel parroting, spinning ball-tarred space monkey window lickers respond with spectroscopy or spectroscopy when challenged with, "How do you know what the sun is made of?" you can now laugh uncontrollably in their crayon-munching faces. Key learning objective number 3. Gases only emit and absorb in bands. This is very important. Number 3, belly laughing train wreck. This is all from NASA. Listen closely. And the spectrum of the sun appears as a continuous spectrum. Really. And is frequently represented as shown below. This type of spectrum is called an emission spectrum because what you are seeing is the direct radiation emitted by the source. In the case of the sun, light is emitted at almost all energies in the visible spectrum, which is why you see all the colors in the sun spectrum. Right? Got that? And here is that famous calculated, created image from Kitt Peak National Observatory from that spectrometer that we've seen up there. This is what they gave us, right? We've all seen this before. Has anyone not seen this before?
I didn't see this before.
No, me neither.
So, this is
John, looks like
I
the gay
did.
flag, by the way.
I've got to admit, I hadn't seen that image before. But it was something I was pondering on. And there's more holes in that than a Swiss cheese.
Oh, is it not the LGBTQ flag?
That's what I said.
My bad, I haven't seen this before either.
Have you not, Nathan? You can't say LGBTQT anymore. It's LBGQTS because they've finally realised that to be totally inclusive, they do need to include straight people as well.
Wow.
Oh, really?
No,
I
I'm
see.
just being sarcastic, but they fucking should, really, shouldn't they? Sorry, move on.
Yeah.
Those are those black holes in that thing there.
All right, this is very important. Listen to this carefully. Also from NASA. When the light leaves the surface of the sun, I thought we were talking about a ball of hydrogen gas. Gases don't have surfaces, people. Okay? But I digress. When the light leaves the surface of the sun, it is very nearly a continuous spectrum. Above it said it was a continuous spectrum. So now it's very nearly a continuous spectrum? Okay. However,
John, that's an
you can
important
think
point,
of it.
John.
okay.
You can brush over that, but that's a complete and utter, total contradiction with regards to the sources of what's being emitted. Now, you can't have a continuous spectrum being received on Earth, surely, and it leaving the sun as a nearly continuous spectrum, but getting to us as a continuous. Or can you, John, in terms of with their supposition of the distance, etc., would they, I don't know, merge or create that? To me, that just seems a big contradiction. They want one, but they've said they've got the other already.
Are you asking Dr. John or QE?
Probably Dr. John first, is it?
I've got no idea, like Adam, and I don't even see how they can say it's the continuous spectrum. You have the sun. Surely they're looking through, like the atmosphere as well. How can you separate out the sun from the medium which you're looking through?
Yeah.
How?
I don't know. I just wanted to point out the slap in the face contradiction just with their words. I mean, this is the tip of the iceberg. This isn't really the problem. Just,
but I don't understand how they can say this is the continuous spectrum. You have the sun. It can't just be the sun, can it?
No, I suppose. Yeah, what you're saying is it constructed of particulate matter on their supposed journey as well?
Well, you have to factor in two atmospheres, right? Because you have the sun's atmosphere. We're in the preposterous ludicrousness absurdity already. Okay? So you have to consider, you got two atmospheres here. You got the sun's atmosphere and you got the Earth's atmosphere and everything in between that isn't what they say it is.
Yeah, I'd leave it, John, Dan, just as that. Their initial starting point is that it's both continuous and nearly continuous as they continue along their mythical story.
Yeah, you can think of it as continuous.
Yeah.
So are we all cool with this contradiction then? So we can move on. I think we're all set, QE.
All right. However, let me say it again. This is from NASA, from the same site as all this came from the same site, right? All this. This is where it ends right here. So when the light leaves the surface of the sun, it is very nearly a continuous spectrum. I'm surprised you guys didn't say anything about the surface, but I digress. However, as it passes...
I'm happy to do so, John. I'm happy to do so, but I think Nathan's moving us on.
John, so... A continuous spectrum. You told me that the continuous spectrums are made not from gases.
That's correct. It's made from solids.
Solids.
Yep.
Yeah, a solid and a liquid would have a surface, but a gas wouldn't, would it?
Yeah, I'm a bit confused.
I am too.
So why is this? Yeah.
There's so many
continuous.
There's so many contradictions here. Listen, we're going to spend all day trying to get through this one.
So are we saying now that the sun's a solid?
Yeah, enlighten us.
That's what it has to be. But one, they're saying it has a surface. So gases don't have surfaces, and they're saying it's very nearly a continuous spectrum. That's what you need. You need solids for that. So there you go. All right. I know it's hard to move on from that, but it gets better, believe me. However, as it passes through the sun's atmosphere, like I said, gases present in that atmosphere absorb specific wavelengths of light, leaving the patterns seen in the spectrum above, right? The spectrum that we just took a look at.
I've got a question there, John.
I can't get through this.
Is that like gases? Because I thought at that temperature, they wouldn't be like gases. They would be plasma.
Oh, you just opened up another can of worms.
I've got another question.
Oh, God.
I've got another question. Surely any gas that was floating on the surface of such a massive body of the sun would be pulled instantly with the force of gravity instantly to the surface of that gas. No, I'm not making sense, but surely you couldn't have a superficial gas surface because, as we know, that obviously when gases get away from the surface of the Earth, the gravity slows them down on such a tiny body as the Earth. Imagine the gravity as a gas tried to leave the surface of the sun. It wouldn't be able to, would it?
Talking about gravitropoloscopy.
Yeah,
Yeah, it's not even my show, and I'm going to have to try and get this train wreck back on track. Right,
It's not our paragraph, Nathan. We didn't
much
write the paragraph.
As much as you want to get into the pseudo-Riemannian four-space time bending and integrate that into this very specific description of how spectroscopy doesn't work, I know it's just going to end up in a conversation that takes at least 40 minutes just to get back to this paragraph. So, well, can for the love of Christ, can we just leave bending of space-time out of this? I'm only just keeping up as it is.
So, like so John, they are like gases, not plasma.
However, as it passes through the sun's atmosphere, gases present in that atmosphere absorb specific wavelengths of light, leaving the pattern seen in the spectrum above. By studying those lines and matching them to known lines of elements, astronomers are able to determine what gases are present. Hey, why'd you flip on me? Right? That's how they do it. It's gases. That's what they're saying. And it's cut and dry. You can't get, if you say gases, then it's gases. Gases everywhere, right? Yep. So
we'll have to try and make we'll have to try and make rhyme or reason in the gaps between these paragraphs, because otherwise we're all going to get completely triggered by these nonsensical doublespeak terms that they're using.
You're telling me that I have to believe, Nathan, aren't you? Just for a minute. Just believe.
Only for the duration of a paragraph.
Yes.
You can think of them like they're gases.
All right. So what we have that paragraph. We have the two paragraphs above and the spectrums from NASA. So we go to Hernshaw, the analysis of starlight at Cambridge, and Jenkins, fundamental of optics. Listen to this carefully. This is very important. Hot, solid objects produce light with a continuous spectrum. Yeah, like I told you above. Hot gases emit light at specific wavelengths. That's partially true. It depends on how hot they are, but I digress. This is the important one. Hot, solid objects surrounded by cooler gases show a near continuous spectrum with dark lines corresponding to the emission lines of the gases. By comparing the absorption lines of the sun with the emission spectra of known gases, the chemical composition of stars can be determined. We have a problem here, Houston. Hot, solid objects surrounded by cooler gases. Are you saying the sun's a solid? It's over. There's so many I can't even. It's such a tangled web of contradictions. It's unbelievable. I can't get out of it. So
the line there, John, is for me is exactly the contradiction here. They're saying that the, and please excuse the vernaculars, the science that's backing up the data that they're collecting from their toilet roll pointing to the sky, right, is based upon the presupposition that hot solid objects surrounded by cooler gases allow you to analyze the emission spectrum, right, of the cooler gases. Now, that's fine, but of course, as we've just rambled for hours, or 10 minutes, the presupposition to require to use that data, any extraction data, and apply it is that the object that is emitting the continuous spectrum is, yeah, lovely, solid.
Last time I checked with the fairytale paradigm, the sun is not solid. I'm just saying. So, like I said,
I thought something else too. I thought that there were no cooler gases around the core of the sun. I think that it would only get hotter.
Oh, we're gonna get to that. That's coming up. So, like I said, is the ball of hydrogen gas, the sun, in the second law of thermodynamics violation, a solid object? No? Then how in the flying Fukuyama are you getting a continuous blackbody spectrum for ball of hydrogen gas? This is what they give us. This is the blackbody spectrum of the sun. Right? We're going to talk about this briefly down below, blackbody radiation, but I digress. I just wanted to show it. So from Lumen Learning, this is going to be good. The dark lines in the solar spectrum. I got a mic open. Thank you.
Yeah, echo.
The dark lines in the solar spectrum thus give evidence of certain chemical elements between us and the sun, absorbing those wavelengths of sunlight. Because the space between us and the sun is pretty empty, astronomers realize that the atoms doing the absorbing must be in a thin atmosphere of cooler gas around the sun.
Hold up. Astronomers realized that, so the next thing is based on an assumption, nothing proven. It's just because the space between the sun is pretty empty, an assumption, astronomers assumed that the atoms doing the absorbing must be a thin atmosphere of cooler gas around, assuming it's round the sun. 3 assumptions in one sentence, I think, there.
Oh, it gets worse.
Yeah, sorry.
No.
Sorry.
No, you're okay.
I was outraged, John. I was outraged for a minute. I'm sorry. It was an outrageous sentence. Carry on.
Thank you. So, dealing with this from Lumen Learning, begging the question fallacy, right? The space between us and the sun is what again? Por favor? And my favorite illustration. All right, folks. Here's what we got. We have the 3 types of spectra that we already went over above. We have continuous over here to the left, absorption and emission. Let's deal with the 2 outside ones and we'll take the middle one last. So like we've said, the continuous spectrum, they're using a light bulb here. Let's just say it's the sun. Well, at least this has a surface. There's a filament in here, right? So if there's nothing between this white light source and you, you're going to get a continuous spectrum. Just the way it is from a solid. Over here on the emission, never mind the second law of thermodynamics, fairytale gas cloud in a vacuum. When this light hits this gas, it energizes it and it gives an emission spectrum. Okay. So what we want to focus on is this middle part right here, because this is what they're trying to have you believe with the sun scenario. Okay, so this is the sun. This is the second law of thermodynamics, fairytale gas cloud. This is you, and you're getting an absorption spectrum. A bunch of scenarios. So, let's say this second law of thermodynamics, fairytale gas cloud is 10 million miles away from the sun and 80 million miles away from you. Going to give you this absorption spectra. No doubt about it. Number 2 scenario. This second law of thermodynamics violation, fairytale gas cloud, is 50 million miles away from you and 40 million miles away from the sun. Are you still going to get the same exact absorption spectra?
Yes.
That answer is yes. Scenario number 3. This second law of thermodynamics, fairytale gas cloud, is 20 million miles away from you and 70 million miles away from the sun. Question: are you still getting this same absorption spectra?
Yes.
Yep. If this fairytale second law of thermodynamics violation gas cloud is 10 million miles away from you and 80 from the sun, same thing, same absorption spectra?
Yes.
If this second law of thermodynamics fairytale gas cloud, you're getting the picture now, is 3,000 miles away from you and 90 million miles away from the sun, are you still getting this exact same absorption spectra?
Yes. I've spotted the pattern.
Turn out the lights. Party's
The
over.
party's over.
Smash
They
it,
say
Riley.
that
Come on.
all pseudoscience
I do have a
must
question, John.
end. You got it. Okay.
I
So,
do
okay.
have a
Do we want to
question,
stop
John.
here? Any comments?
Yeah.
Yeah.
I noticed that in this conversation tonight, you've digressed an awful lot in yours. You used the phrase "I digress" a lot tonight. I've never noticed you use that. I'm going to ask: have you been watching Jay's 2 Cents?
Negative.
It's just that I've never heard you say the phrase "I digress," and Jay's 2 Cents always says it. So I presumed that you must have been watching it because, well, I've never heard you digress before.
Don't be punking out
He's
my
got a strict
digressions,
regimen
man.
tonight.
Must be a correlation.
It must be a correlation.
Don't be punking out my digressions. I never heard of that guy, and I've used digressions before. You just don't listen to
Never
my
heard you
presentations.
No, I've never heard you digress before. Anyway, sorry, carry on.
All right.
This is a Coriolis fallacy. Come on.
All right.
Don't move on. I've got my own. This is when I listened to this in midweek. It confirmed my less detailed, and it's the same conclusion, but a less detailed analysis of it. And I always, from my understandings of the presentation of the spectra of the sun and the absorption spectra were presented, I always, and you heard John E chipping in at the distances, and I always thought, well, it doesn't make a freaking difference, does it? What's being analysed, or where what's being interrupting the continuous spectra is interrupting it, really doesn't matter. As long as it's being interrupted. Now, I was happy with that. And then recently we've been rambling, haven't we? As ballers talk about the effects of gravity in relation to elastic collisions, and how somehow this is the causation of why at the top layers of the atmosphere there's only hydrogen and helium. I've just got a quick question for you, John. This absorption spectra that's shown in terms of direct sunlight, what molecules does it show are absorbed in terms of the supposed cool gas layer around the sun?
Is that Dr. John D or QE?
I don't care which John it is.
Well, we're going to get into a big problem here with cooler gases, right? And like I said...
No, not the cooler gases, but the gases that they suggest from the absorption spectra.
Right.
What are they saying those gases are?
It's mainly hydrogen and helium, like we observed it above. Right?
Yeah, but I'm not sure whether you can actually say that specifically, because if John scrolls like back up to that huge like sun there. So I don't think you can specifically say that. You can just say there are certain bands we can't see. But but why can't we see those bands?
Oh, hold up, John. That is that a secondary criticism of the spectra, or a criticism of the analysis that they portray? So what they say analysis. That spectra is, So they, but forget. So let's just forget that for a minute. They say that the gas cloud around the sun, the cooler gas cloud, which is creating the absorption spectra, is created by hydrogen and helium.
Yes, that's what they say. Yes.
Yeah. So I've just got one final question then. Because you can't draw any inference, but because this is a completely unrelated topic, again, based on their presupposition, but what do they say are the main constituents of the top layers of the atmosphere?
Top layers of what atmosphere?
Of the spinning ball Earth.
Right. Great question.
Hydrogen and helium.
Okay. And now, given the fact that you've just described that the distance of whatever cooler gas cloud is irrelevant, between the distance between the observer and the source is irrelevant. Now, we obviously have never been able to, even in their model, confirm the constituency of the cooler gas cloud around the sun. So we don't know that. But what we do know is that the top layers of our atmosphere in their model, it's comprised of the same absorption spectra that is displayed.
So I'm not sure what you're saying there, Adam. So are you saying because the top of the atmosphere is like supposedly hydrogen and helium, no matter which star we focus on, we will get hydrogen and helium lines?
Well, I'd say to you, John, if there was no cooler gas cloud around the source of the sun, right, and there was nothing there, and it was all the presupposition we've given, and the only barrier between the observer and the direct source was the hydrogen and helium in the top layers of the atmosphere, what absorption spectra would we get?
What you really need is somebody like Edmund in Narnia to confirm this from the second law of thermodynamics violation. So if only there was some special band of wizards with special costumes and funny hats that went up on rockets that could give you this answer. Is there such a...
There's another layer, Nathan, to this. There is one more actual logical presupposition that I want to ask. So it would give us that absorption spectra, John, yeah? As described, whether it was at 10 million miles from the source, in the middle, or either way, yeah?
Yes.
All right. Now, if this is the only defense for the ball, if there were two cooler gas clouds, one around the sun and one in the supposed atmosphere of the spinning ball Earth, would the absorption data look any different?
No.
No. So that's its only defense in my book. But the only one we can prove is the one that when we go to the top layers of the atmosphere plane and measure it, we see that maybe possibly slight change. I've never confirmed it, but who knows? That even in their model, that's the only confirmable one. But yeah, there endeth my ramble on that.
Yeah, we're gonna get into some big bad problems coming up here.
Cool.
On B, cool thin gases around the sun. Friggin' where? The photosphere, what they call the surface, gases don't have surfaces for the 20th time, said to be at 5,700 degrees Kelvin. The sun's atmospheric layers, which are the chromosphere and the corona. You tell me if these are cool thin gases. The chromosphere is said to reach 500,000 Kelvin and is 10,000 kilometers thick. And the corona is upwards of 10 million Kelvin and is 5 million kilometers thick. So, does this, when you hear cool thin gases, is this the mental picture that you get? That's rhetorical, by the way. Rochester Institute of Technology. Thin gases emit light of only a few wavelengths. Call this an emission or bright line spectrum. If there is a source of light behind it, a thin gas will absorb light of the same wavelengths it emits. We call this an absorption or dark line spectrum. Again, are the atmospheric layers of the sun cool or cold? How about thin? You wouldn't think so, right? So, let's allow Professor Nicole Vaught of New Mexico State University speak to this and hammer my points home. Ready?
So now that we have the idea of colors going through the spectrum and of a larger spectrum that colors shorter wavelength or of longer wavelength than the human eye can, we're going to take those ideas, apply them spectra, figures or plots showing the dispersed light spread out as a wavelength. And we're going to consider the astronomical applications of spectra. So we begin by building on the atomic theory that we developed last week. We know that a given atom of some species will absorb and emit energy at the same frequency. So if it absorbs a photon at a particular frequency and has an electron jump up one or several energy levels, inevitably it will emit the same radiation when that electron jumps down to lower or ground state. A cool gas of hydrogen atoms produce an absorption line spectrum that lies between you and your telescope and a continuum. So let's think about this and develop this. In our first diagram, on the left we have a white light source, something that emits continuum radiation at all frequencies. And then we have a gas cloud, cooler than the star, and is filled with atoms, represented as small circles. Our white light source, if observed directly, would produce continuum radiation at all frequencies. But what happens if we look at the star through the cold gas cloud? We know that the cloud is full of atoms. When we say that it's cold, we mean that the atoms contain electrons that are in low energy states, which would just love to jump up to higher energy states. So we see colored beams of radiation are in all colors, meaning that it's emitting light at all wavelengths or all frequencies. Those photons, which contain exactly the right amount of energy to enable electron gas cloud, energy level to energy level, are the ones which are absorbed by the gas cloud. So when we look at the star through the gas cloud, we see a continuous radiation source, light preferentially removed or absorbed at those key frequencies. So this is like a fingerprint. Once you match up the wavelengths that are missing from the continuum spectrum, you know exactly what elements are present within the cloud. Now you may wonder why the radiation beam of light emitted from the star when you know that the atoms in the gas cloud will be excited and de-excited. Let's think this through carefully. The electrons are elevated to a higher state within the atom, and then, given a little bit of time, so in essence, all of the atoms in the cloud are absorbing and then re-emitting the energy which they are. If that's the case, why doesn't that energy just fill in back the holes in the spectrum, causing us to see a perfect continuum spectrum? Right. The answer is very simple. Once an atom absorbs a photon, it loses all of the information about the direction in which the electron absorbs the photon, takes that energy to climb up to a higher energy state, and then when it falls back downwards, that photon is re-emitted in a random direction. This is the key point. And the result of this, the gas cloud emits that radiation isotropically, meaning in all directions. It doesn't send all of the photons back along the beam of the star in the direction in which they were traveling before they were absorbed. Instead, they get scattered in all four directions. We can see this by placing another telescope, one that only looks through the gas cloud, but that does not see the star. Imagine that the star and the gas cloud are separated by quite a great distance, as are the telescopes, so that we only see very narrow beams, much as when you look up at the sky, one individual star only covers a very small. Now with our second telescope, when we look straight through the gas cloud, what do we see? Well, if there's no strong source of radiation present, if there's no star, we don't see anything. The cloud is cold, remember. And what that means is that it's not emitting energy on its own. The situation gets more interesting when we add back in the source of continuum radiation left. Once we do that, our gas cloud has a ready source of energy. It starts to absorb photons and re-emit them. And because it's re-emitting them in all directions, some of them are going to fall into a line that points to our second telescope. We don't see the continuum radiation from the star that passes through the gas cloud. What we see is only the radiation re-emitted by the cloud. So what we see now is an emission spectrum. At most wavelengths, there's no energy whatsoever. But at a few key wavelengths, those that correspond to the energy levels of the atom within the gas cloud, we have extra light. If you combine this emission spectrum with the absorption spectrum we get by looking at the star through the cloud, the combination, in effect filling in the holes in the absorption spectrum with the emission spectrum, leads us to the original continuum spectrum. Light may be divided into two paths, but it's neither created nor destroyed in this process. Very elegant.
Yes, it's very elegant. In conclusion, the pseudoscience priest hijacked a legitimate discipline, spectroscopy, soiled, twisted, and bastardized it to belly-laughing superficially comport to the mother fairy tale, their heliocentric spinning ball space monkey religion. Comments, questions?
Yeah, I've got a question. The yeah,
Johnny,
the
need to
layer.
knock off B1.
What's the problem, Anthony?
Knock off B1. We can hear ourselves talking back to ourselves.
No, you shouldn't. It should be good to go.
Hello. Now I can hear an echo.
Are we good?
I think
Hello?
so, yeah.
Okay.
Hello.
No.
No.
Whatever you change to play the video, just change it back again.
I haven't changed anything.
Okay. Maybe it will just dissipate if we continue.
No.
For you, sound good now.
Okay. The convoluted mess that was that description of measuring the reflections from clouds at a different telescope. I was thinking, why is this taking so long? And then it suddenly dawned on me halfway through her explanation that it's the biggest load of convoluted nonsense I've ever heard.
And I have a question here. Right, so if we need a thin layer of hydrogen gas, that's, cold, would you say that that thin layer of hydrogen gas is going to be on the surface of the sun or within Earth's atmosphere?
I could only presuppose, as I probably alluded to earlier, the thing that came out of what the eminent professor obviously was talking about is, and this diagram's a great explanation of it, is we could probably do this setup with regards to any thin, cool layer at the top of our atmosphere plane and get the correct emission spectra that would match up with the absorption spectra. Oh, other way around, sorry. Doing my head in them too. But on one, however, with regards to validation of results, are they ever going to go and line an optical instrument up in line with the thin layer of this thin cool, of which QE described a few layers of gas they presuppose, and none of them sounded thin or cool. But even if they did line them up with those, have they done that to validate anything to support this nonsense?
I don't know. You tell me. This is, like I said before, all this is preposterous, ludicrousness, absurdity within a preposterous, ludicrous absurdity. Before asking me questions about this, hard to get the tangled web. All I have to do is go back to all the friggin' presuppositions that train wreck this thing that are not true, right? They contradict themselves with every other statement. And like I said, they've taken a legitimate discipline and exploited it and bastardized it for their own use. And they're busted. I mean, there's no other way out of this. You're busted. You're finished. It's over. And astronomy,
I've got a question.
Hold on a second. Astronomy, astrophysics, and cosmology depend 99.98% on what?
Observation.
Celestial and astronomical spectroscopy. Turn out the lights, baby, because it's over. Thanks.
So, quick question for Dr. John D. In all of your studies and tests, if you were doing a thing where you were taking, say, an object and you wanted to analyze from its emission whether there was any gaseous significant layer around it, but in doing so, just in front of the sensor, you put the exact same layer of gaseous mixture in front of the sensor, would any results you collected have any validity with regards to your supposition of what was around the light source?
No, they wouldn't, like, would they? No. No.
No.
You'd have to know, you know what's in front of your sensor.
Well, that was the
Yeah,
question
I said I
earlier,
covered this
Todd.
earlier. I was going to say I covered this earlier, right? You just need an equivalent of Edmund actually in Narnia, or in this case, a correspondent in the second law of thermodynamics violation. If only there was such a group of wizards that could provide you with that data to back your supposition.
This is just a train wreck. Just this picture here. I mean, what, like what's going on? I don't understand. Is that meant to be like? Is that meant to be, like a gas halfway between the star?
Yes.
And halfway between like the telescope?
Yes.
It's like what's going on? Like the gas wouldn't be there. Yes, in a so-called vacuum. What is going on? It's just ridiculous. It's ridiculous.
Yeah, even given them their fairytale gas cloud and the second law of thermodynamics violation, they're train wrecked. They're train wrecked in so many. Like I said, it's a spider web of train wrecks. Each lane you go down, a train and a flamethrower waiting on you. So they're done. They're finished. This is a joke. So let's move on. Let's wrap this up with two small subjects. I'll go through this quick. We'll touch on Kirchhoff's law of thermal emission or black body radiation. This requires opaque cavities to produce black body radiation. Does the sun contain opaque radiative onion layer cavities? In elephant tears is a colossal understatement. Number 2, Kirchhoff's law of thermal emission, black body radiation, is only valid in thermal equilibrium. So, is the sun enclosed in a box? And in that box, is the sun and its fairytale radiative onion layer cavities in thermal equilibrium? That's what they call these layered cavities between the core and the convective zone of the sun. So you're aware. According to the standard model of the sun, does the sun have a convection zone? Then how in the flying Fukuyama can it be a black body, por favor? In summary from this section, the sun and its spectra have nothing whatsoever to do with black body radiation. Friggin' duh. Amoeba farts are more relevant. So, quickly. In 1860, Gustav Kirchhoff came out with his black body or law of thermal emission. What they used to do back in the day, they used to have these boxes and they lined them with lamp black. Okay, the inside of these boxes. Well, this expanded carbon, right? And what would happen, they would wait for a little bit, and that carbon is a good emitter and absorber. Well, it would overwhelm the box, the radiation would come out, it would come out, and it could spectrum, right? So Kirchhoff supposed that, well, it won't only work with lamp black, it'll work with any material, right? That was his supposition, that any material, you're going to get a continuous black body spectrum, no worries. However, he put a perfect reflector. He lined one of these cavities with a perfect reflector, right? And he sat there and waited and waited and waited because, well, it's a perfect reflector. You're not going to get anything out of there. So after waiting a long time, he said, more or less, the heck with this. And he put a piece of charcoal in there, thinking that the charcoal, carbon, was a catalyst. So what's going to happen when you put a piece of charcoal in a black box with a perfect reflector, right? The charcoal's going to emit, right? The reflector is going to bounce all those ways back into the charcoal. It's going to re-emit. In a very short time, it's going to overwhelm the box, and you're going to get a continuous black body spectrum, right? No. The charcoal isn't a catalyst. It's the cause. So this entire fiasco, black body radiation, all this spectroscopy stuff, let me be specific, astronomical spectroscopy, stellar spectroscopy, all this utter inane bollocks. It sends astrophysics back to the days of Asclepius, right? And tune in Thursday, because I go into this a little bit further with my CMB background presentation that I just pummel into the incoherent oblivion. So stay tuned for that. All right. Let's end on a positive note. 1 John 1:5. 1 John 1:5. This then is the message we have heard of him and declare unto you, that God is light, and in him is no darkness at all. Revelation 21:23. Somebody's off mute. Go on mute, please. Thank you. Revelation 21:23. And the city had no need of the sun, neither of the moon to shine in it. Uh-oh. Isn't this redundant? If the sun or the moon reflected sunlight, why would you need to mention the moon here? All you would have to say, and the city had no need of the sun. This is redundant. If the moon is reflecting the sunlight from the sun, right? Yeah, but I digress. So, and the city had no need of the sun.
That's not a digression, John. I like that one.
You like that one?
I like that one. That is a distinct. You need Anthony Riley on this. Tony, is that a distinction, or is that a link? That seems neither one or the other. You don't need one or the other. It's not aligning that one is derived of the other, is it?
No.
Yeah, exactly right. So, and I'm going to go into a deep discussion of this in a future presentation about the moon reflecting sunlight, and we're going to pummel that into the incoherent oblivion too. But I'll stay on topic with God is light, and we'll continue. And the city had no need of the sun, neither of the moon to shine in it, for the glory of God did lighten it, and the Lamb is the light thereof. So basically, God is light. Meaning of numbers from BibleStudy.org. The number 7, used 735 times, 54 times in the book of Revelation alone. Let me tell you what, this is a serious lowball. I don't think it's 154. I think it's more. I think you could spend a lifetime in the book of Revelation and not find all the indirect sevens that are used. But I digress again, Tony. Used 735 times. The number 7 is the foundation of God's word. If we include with this count how many times sevenfold and seventh is used, our total jumps to 860 references. 7 is the number of completeness and perfection, both physical and spiritual. It derives much of its meaning from being tied directly to God's creation of all things. According to some Jewish traditions, the creation of Adam occurred on September 26, 3760 BC, or the first day of Tishri, which is the 7th month on the Hebrew calendar. The word created is used 7 times describing God's creative work. There are 7 days in a week, and God's Sabbath is on the 7th day. The Bible as a whole was originally divided into 7 major divisions. They are 1, the law, 2, the prophets, 3, the writings or psalms, 4, the gospel and Acts, 5, the general epistles, 6, the epistles of Paul, and 7, the book of Revelation. The total number of originally inspired books was 49, or 7 by 7, demonstrating the absolute perfection of the Word of God. Point being, from sciencejrank.org, 7 colors constitute white light: red, orange, yellow, green, blue, indigo, and violet. Students in school often memorize acronyms like Roy G. Biv to remember the 7 colors, the spectrum, and their order. So people, it's hidden in plain sight. He's there. He's waiting for you. Thanks for your ear. Have a nice day. Questions, comments?
Richard of York got boiled in vinegar.
You do it
Gave
that way.
battle in vain. Gave battle in.
Yeah, but we turned it to got boiled in vinegar. To remember the ROYGBIV, John.
I just remembered.
Funny.
I just remembered Roy G. Biv.
John, yeah, I think we should just like say, to people who who will hear this, that spectroscopy does have its uses. It should just stay within, spectroscopy should stay, within labs where it's useful.
Oh yeah, that's what I was saying before.
Yeah.
Like I said, the pseudoscience priest hijacked a legitimate discipline, spectroscopy. Nothing wrong with it. It's soiled and twisted and bastardized it to belly laughing, superficially comport to the mother fairy tale. That's it. That's all they did. That's all they ever do. That's all they can do is try to bastardize things and twist them into their paradigm. And it just doesn't work. We exposed it. Nothing wrong with spectroscopy. All right, guys. Any final thoughts? We'll go around the room. Betty?
Not really, no. I have to let it work on me a little bit. So, yeah, it's interesting. I think there's a lot of fallacies in the whole, and assumptions and things that they should figure out how to get out of this, and I don't think that they can. So, interesting.
The distinguished Nathan Oakley, final thoughts, sir?
It's been very educational. I've really enjoyed it. I mean, I now know the distinct difference between controlled environment spectroscopy, which is what a spectroscopist would be engaged in, with closed environments under great degrees of control, versus looking at the emissions from clouds on a second telescope when you don't know the medium you're looking through, and calling it spectroscopy because they want to assert their pseudoscience religion with some degree of validity. So they've, as you put it, hijacked a genuine, legitimate field of study so that they can assert it in their pseudoscience religion. It's been extremely educational, thanks to largely yourself, Adam, and Dr. John. So thanks.
Adam, sir, final thoughts?
I think I'd probably echo Nathan's sentiments there. To me, hopefully you've highlighted tonight how a perfectly scientifically validated piece of technology, which is used to gather fantastically validated empirical results, how that solid bit of, like I say, technology and science that works here has been hijacked, and all of the validity that data gives has been hijacked by pseudoscience to support the kind of waffle and presupposition and just complete fairy tale nonsense that is their construct. And hopefully, like with your presentation and Dr. John's validation of your supposition, so there's no silly little arguments that can be had about the actual context of what's been said and the implications of it. People do understand there is a huge difference between spectrochocoloscopy and actually spectroscopy. And I think John probably the best to speak, because it's his actual practice, his discipline that's being insulted here from me. If somebody, as you said, Nathan, was saying, yeah, I waved the magic wand over it and said this is medicine, I'd be equally outraged. So over to you, pal.
Dr. John D., sir, final thoughts?
You're on mute.
Right, sorry. Yes, they have like taken spectroscopy and they've twisted it to just like push what they want like people to think. But more importantly, I have one question: the sun. So is the sun like solid or like gas? I'm very confused.
So are a lot of people right now, because we need an answer to that question. And it better be logically consistent and practically consistent with the rest of your story, or we're going to bust you. We're going to bust you right in the teeth. So you better get it right. This is pissing me off. I don't know about you guys. Listen, I am friggin' pissed. I was pissed when I was going through this presentation originally and making this up. I got pissed. I don't understand how you can't be just outraged. I don't get it.
I'm not outraged, mate, because the best data that they can fake with their rocket satellite analysis nonsense says that we've got a continuous spectra. So that's absolutely fine, because the best fake data they've got is actually in opposition as to what they say the thing's made of, because they say it's made of a gas. You can't get a continuous spectrum from a gas, so which one do you want? Your data or your belief?
Yeah, it can't be reconciled, man. They can't do it. They're not getting out of this. So, Anthony, final thoughts, sir.
So, what do we say to ballers when they say spectroscopy and they give us that one word, all-encompassing phrase? What's the one line we respond to them and say, hang on a sec?
I got one. You're a bonehead Dunning-Kruger pretender clown. That's my response. And point them right to this presentation.
I had somebody literally pull the spectroscopy card on me tonight. I might go back and edit my comment and just say you're a pretender clown.
Oh God, I just can't believe just like what a farce this whole thing is. What a worthless. It's just worthless.
Yep.
All right, guys. Thanks for coming. I'd like to thank my entire panel. Just putting up with this. Now, this was new to a few members on the panel, but old hat to a lot of others. For you out there that this is new to you and you first seen it, I can't wait to see the comments below. I really can't. So, take no prisoners. No quarter will be asked, none shall be given. And remember, I'll be back.